Okay, so this is exercise 13 out of your packet. And what I'm going to do here is I am basically, let's look at the problem. It says, in a certain experiment, I've got 28 mils of a 0.25 molar solution of nitric acid and 53 mils of 0.32 molar of potassium hydroxide are mixed. Calculate the moles of water formed. Does that look hard? That's not hard. So let's do it exactly how we did it. Yeah. So let's write our equation first. It says that I have nitric acid. I've got potassium hydroxide. That goes to potassium nitrate and water. Now what's interesting about this is, sorry, that's a liquid. That is not a solid, it's a liquid, right? That's sort of our product. That is our, it's not a precipitate, but it's not an ion either. So if I were to write out all of my ions and write my complete ionic, three goes to water, liquid. You can ask questions if you want, it's fine. All right, do you see what I've done here? This is like my precipitate. I get rid of all my spectators, and I even have a net ionic equation. So if it's going to ask me how many moles of water I'm going to make, it's just exactly what we've always done. You can either go through the net ionic equation like we did on day 1. I'm going to go through this equation like we did on day 2. Okay? All right. So I'm going to rewrite the equation here so that I can put all the chemical quantities underneath. But I just wanted you to see this is not any different from what we have been doing all along. Okay. So what do I have? Let's put our laundry list under here. I have 0.028 liters of that, and it's 0.250 molar. And I have 0.053 liters of that, and it's at 0.32 molar. And I want to know how much of that I have. So let's get started. We're going to do exactly what we did yesterday. Let's start with nitric acid. Okay. And so I'm going to say I have 0.028 liters of nitric acid. And 1 liter of nitric acid is 0.250 molar of nitric acid. All right. Now, the problem also asks for the concentration of H plus and OH minus. It doesn't ask for the spectators on this one. We're just going to look at H plus and O minus. So remember how we stop here. We calculate what this value is. This is mole HNO3. Now that I know how many moles of HNO3, I know that HNO3 goes to H plus and NO3 minus. So if I have 0.0070 moles of HNO3, how many moles of H plus will that be? 0.007. So let's put it up here. Let's put it up here. I have 0.0070 mole of H plus, and I have the same amount of nitrate. I could put that up here. I'm not going to use it in this problem. But there we go. There's all our stuff. Okay? But that's not what I want. I don't want moles of nitrate. What do I want? Moles water. In fact, they're not even asking for grams in the end. So I know that 1 mole of nitric acid gives me 1 mole of water. So that's 0.0007 mole water. Okay, that's 1. Everyone's got that, right? Just like yesterday. Let's do the potassium hydroxide now. Okay, so here we go. Now the end of this is going to be super short. 0.0530 liters. 1 liter of potassium hydroxide is 0.320 mole. potassium hydroxide equals 0.0169 mole potassium hydroxide. All right. If I know how many moles of potassium hydroxide and it does this, then how many moles of hydroxide?
0.0169.
Correct. So I'm going to come back up here. 0.0169 mole OH.
Could you round that up to like 0.02? Or would you?
That's a great question. Technically, what I would do, wait to the very end, because if you start rounding too early, it can mess up your numbers. But I've seen that on a lot of papers. Use all the sig figs that you have. Always remember that. Remember, empirical formulas too were like that. In general, when you're doing long problems, like if it's long FRQ, that's what you'll do. Okay, so that's not what I want though. I want moles of water. So 1 mole potassium hydroxide is 1 mole of water. And where am I getting that from? I'm getting that from right here, right? 1 mole of this gives 1 mole of water. 1 mole of this gives 1 mole of water. That's where I'm getting it from. Okay? So in this case, I get 0.0169 mole water. So this is my limiting, right? Now, the problem asks, what are the concentrations of H? So it asks you also, how many moles of water do I make? That many. Whatever one's the smallest. It doesn't ask for mass. It doesn't ask for grams.
It's 0.007.
Yes. Now, if this is limiting, how many moles of H plus do I have left at the end of the reaction?
Like point something 30.
Well, I have, right. I used it all because this is my limiting. So here's the way to remember it. For your limiting, if this is my net ionic, any ion that is in the net ionic, in the limiting compound, is done. It's 0. OH is not in this one. H plus is. It's gone. Because I used it all. That was my limiting reactant. I used it all. Yes?
So that means that we can only calculate the concentration of OH?
Correct. Let's do it. So OH is going to be easy. Remember, it's going to be start minus used, right? That's how I'm going to do it. Well, what's my start? I have it up here. My start is 0.0169. I put it up there, 0.0169 mole. How am I going to find out where all the other OH is? Where did it go? It made water. So if I need to take the thing it made and find out how much I used to make it. I made 0.0070 mole water. So there's 1 mole of water gives 1 mole OH minus. That's here. 1 to 1. So that tells me how much OH is in here. And that turns out to be 0.0070 mole. So I pull that up here. Mole. And that gives me 0.0099 mole. Now, what I could tell yesterday, a lot of people made this mistake. They stopped here. That's not a molarity, is it? All right. Well, some people forgot this part. That was one mistake. The other one is people forgot, oh, okay, those are moles. I got to divide by my volume. What is my volume here? 81. So I'm going to divide this by 0.81 liters, and I get 0.123 molar. Whoa, can't see it. There it is. All right, so if you notice, it's all the same as what we did before.